Okay, do we have a question? Do we just have extra credit and exams? Yes, that's correct. No assignments. Okay. So what we'll do is I'll see how we're doing grade wise after the midterm is graded. Okay, if I need to bump up the extra credit a little bit, I will do that. It's really just dependent on how the grades look after midterm. Typically, I don't need to. Okay, I don't need to bump up the extra credit because everybody does just fine. Okay, but I can't say that for sure because you guys are obviously different, different, a different class. But yeah, we'll take a look at it after the midterm.
I have a question.
Go
Um,
ahead.
how much of what's on the extra credit, the pre-lecture quizzes, is going to be on the actual like midterms and finals?
So, I mean, some of it will be, but here's the basic thing about the tests. Okay, you're going to just get you're, you're going to get 50 questions drawn from probably 800 questions. Okay, so it's really just kind of hit or miss. I guess the important thing, going into the midterm is that you understand the concepts, the basic concepts. Okay, um, we do a significant amount of just basically defining things, which is just the nature of the beast. Where I'll just define what certain things are. But when we talk about concepts, and I'll be talking about that an important concept today. Those are the things that you'll want to be able to understand the concepts because a lot of the questions are going to ask you to kind of apply what you know. Then there's going to be other questions that just say, what is this? This is the definition or whatever. What is the thing that I'm talking about? So yeah, it's just kind of hit or miss. So I guess the short answer for that question is yes. The the questions in the extra credit tend to cover or tend to be on important topics. Okay, so what I'm trying to do is set it up so that those of you that take the extra credit, you're going into your book and you're learning about these topics. Okay, you're at least reading the book and taking the extra credit before we do lecture. Okay, so that's kind of how that works. Okay, so we will talk about the exam when we get closer. Okay, it is going to be, yes, it'll be a combination of multiple choice, probably mostly multiple choice. There might be some true false, um, maybe fill in the blank, maybe one or two short answer type situations. Okay, but I'll reiterate this. Okay, it's going to be open book, open notes, so don't stress out about it. The important thing is that you just attend lectures, listen to me talk for an hour, and I'll go over the important stuff, and you'll understand. You'll understand the material when the exam comes along. So you won't really even need to delve into the book. Quite frankly, there will probably be a lot of questions that you already just know, and you won't even need to reference it. Okay. So we'll talk about the midterm well, let's see. The midterm is going to be late March. Well, I guess maybe mid-March. So we'll talk about it early March. So here in a couple weeks. Okay, anything else other than stuff relating to the midterm? Okay. All right, well then let's dig in and talk about volcanoes. Yeah. All right. So here's one of those important concepts. Okay, I'm going to be talking about basically the composition of magma, and we're going to be differentiating between different types of lava and why they're different. Okay, so in order to understand both what lava is and how it behaves, we need to understand some things about it. Okay, first and foremost, we need to understand what viscosity is. Okay, you're familiar, most likely familiar with viscosity as in engine oil. Okay, same exact concept. So viscosity is a measure of a material's resistance to flow. Okay, so this is like taking a board, tilting it up at an angle, and then dropping some sort of liquid down onto it. Okay, if it's water, you know that water is going to run right off. It's going to flow very easily. But if you drop honey on that board, it's going to just very, very slowly move in downhill direction, right? Okay, so that is what I'm talking about with viscosity. So when we have materials, in this case, we're going to be talking about lava. Okay, when lava has a low viscosity, that means that it is a runnier lava. Okay, so it's not, it's not as runny as water, but it's a more liquid lava. Okay, and that's this type of lava over here in this right side picture. You'll notice that it's kind of flat like and it spreads out pretty easily. Hey, that's exactly what happens with water, right? When you spread water out, it's still kind of flat and it spreads out. Okay, now then you have high viscosity lava. Okay, that is lava that is very thick. It's like, kind of like thinking of it as honey. Okay, so one thing that you'll notice with this specific type of lava here is that it's not flat. Okay, it is clearly upward at a pretty decent angle. Okay, and it also looks jagged and angular compared to this one over here, which looks kind of like smooth, ropey type appearance. So we know that this type of lava here has a very high viscosity. It's a very thick lava, and when it solidifies, well, I'll leave that part out, but it's just very thick, and as a result, it can build up into what looks like kind of a wall. Okay, so that's very, very important concept. Okay, so we're going to look at factors that affect viscosity, and I'll tell you right now that the viscosity of magma or lava, whichever you're looking at, really plays an important role with the violent nature of an eruption. Okay, so viscosity determines how violent a volcanic eruption will be. Okay, I'll talk more about that here later on in this presentation. Okay, so some other factors that affect viscosity. Okay, composition is an important one. By composition, I mainly mean how much silica content. Okay, that is very important. How much silica content really determines how thick or how thin. Well, basically, it determines whether viscosity is high or low. Okay, so whether it's going to be runnier or thicker, silica is really what is very important with that. Okay, so high silica content, we know from looking at rocks that the granitic or the felsic rocks, the light colored igneous rocks here, they are the ones that have a high silica content. And thus, when they get melted down into lava or magma, it's that type of rock will result in a magma that has a high viscosity. Okay, Over here on the other end of the spectrum is the basaltic rocks or the mafic rocks. We know that the silica content is lower, and as a result, these rocks will melt and turn into magma or lava that has a low viscosity. So this type of lava will be more runnier when compared to over here. Okay, and the andesitic one is just kind of in the middle. Another factor that affects viscosity is temperature. So basically, hotter magma or lava is less viscous. Okay, so that means the more you heat up the lava or the magma, the more fluid it becomes. Okay, and flipping that in reverse, the more it cools down, the thicker the lava will get. Okay, so the more viscous it will become. Okay, also another thing that affects viscosity is the presence of dissolved gases. Okay, those are also called volatiles. So basically, volatiles really consist typically 1 to 5% of the volume of a lava. Okay, and it varies depending on which type of lava it is. But basically, the gases that are associated with these volatiles are predominantly just water vapor followed by carbon dioxide. So mainly those two gases, but there are also other gases that are found in smaller quantities, including some pretty noxious gases like carbon monoxide, the gas that kills you if that's associated with internal combustion engines. Sulfur, that rotten egg smell. Okay, so and then there's others as well. But I just want to tell you that when it comes to lava, the dissolved gases that are found within that lava are mainly going to be water vapor and carbon dioxide. Okay, now when magma is coming to the surface from deep down, what's happening is the pressure surrounding it is becoming increasingly reduced. So the pressure is lowering. Okay, think of it as like when something's buried deep. We know there's a lot of pressure on it. Okay, let's say you bury a box, a time capsule or something. Okay, you're gonna dig a hole, put it in there, and then dump soil on top, right, to bury it. Okay, well, all that stuff has weight, and that weight or pressure pushes up against the object. Okay, so same thing works with magma. You have tremendous pressure pushing against the liquid magma when it's below Earth's surface. As it comes up towards Earth's surface, the pressure naturally decreases. Okay, and then once it reaches Earth's surface, a lot of pressure is released. Okay, because there's no longer anything pushing up against it other than air, and air just doesn't have much pressure. But as a result of that loss of pressure, or reduction in pressure rather, the gases, these volatiles, they have a tendency to expand. Okay, and it's that expansion oftentimes results in the violent nature of an eruption, but oftentimes it just results in just that additional additional assistance, I guess, let's put it that way, additional help for that lava to get shoved up on the surface. Okay, so as the pressure just kind of pushes it up on the surface. Okay, so that's pretty much what I mean by expansion provides the force needed to extrude lava. Okay, remember, extrude means just to go from inside to outside. Okay, so up on Earth's surface. And then a pretty important thing is that the violence of an eruption, so the violent nature of an eruption, is really determined based on, well, both the silica content and how easy gases can escape from magma. Okay, and those two are related. So I will tell you that with very very high viscosity magma, so the thick magma or lava, gases have a difficult time escaping because the magma is thicker. Okay, makes sense. Whereas the easy or the low viscosity magma, the volatiles have an easier time basically escaping because the liquid lava isn't as thick, it's more runny. Okay, so that's why the higher viscosity magmas have a tendency to produce a more violent eruption as opposed to the low viscosity ones. Usually the low viscosity ones don't even have a violent nature at all. Oftentimes they will just either just kind of bubble over, or they'll shoot out as a fountain-like appearance, which you've probably seen pictures from Hawaii. Okay, so here are the two types of lava here. Okay, so we looked at this picture earlier. So what we have here in picture A is called A'a. Okay, this is a very viscous lava, so it's very thick. Okay, like I said, rough, jagged. You can't see it, but there's a lot of trapped air gas bubbles within the lava itself. And you know that it's very viscous because it basically creates a straight up wall almost. Okay, now when we move over to this one, this is called a pahoehoe. See that smooth, ropey, just kind of flows downhill under the influence of gravity. Okay, it's not jagged or anything like that. Okay, that's the low viscosity lava. Okay, now the pahoehoe is typical of like Hawaii. Okay, so it's pretty runny stuff. Over here, the A'a is pretty typical for like subduction zone environments, so like convergent plate boundaries. Okay. Yeah, and then I already talked about gases. So it's so 1 to 5% of the magma or the lava is going to be gas. Vary. Okay, so before we move on to looking at the material itself, are there any questions about the viscosity or composition of lava? Okay, there will be a chart at the end of this lecture that summarizes all this stuff. So I'll recap when we get to the end of the lecture. Okay, so let's talk about the material that's produced by a volcano when it erupts. Okay, in general, this material that's ejected from a volcano when it erupts is referred to as pyroclastic material. Okay, now pyroclastic material it's just any material of any size. Okay, but really pyroclastic material gets kind of broken down into more easily to manage categories, and those categories are differentiated generally by the size of the material. Okay, so the pyroclastic material ranges from ash, okay, which is very fine, often silt-sized, basically glass fragments. If any of you have ever felt true volcanic ash, it feels very abrasive if you rub it between your fingers. Okay, and again, that's because it's essentially silt-sized glass fragments, very tiny glass fragments. Okay, because remember, quartz, or well, silica in general, which quartz is made of, is what glass is made of. Okay. Okay, so that's ash. That's the smallest on the spectrum. Then you get cinders. Cinders are about pea-sized. Lapilli are walnut-sized material. Okay. Then pumice is a rock. So let me skip that for just a minute here. We'll come back. Material, the largest material. Okay. You have bombs and blocks. Okay. So bombs, which are down here, are around cobble-sized material. And I know we haven't talked about sizes of sediments yet. We'll get to that here in a couple weeks. But yeah, basically cobble size. So like kind of like a type of rock you would find on the stream, that kind of size. And then there's blocks. Okay, those are basically anything bigger than a cobble. Okay, ranging anywhere from slightly larger than cobble size all the way up to could be as large as a house, okay, or a car. The chunks, chunks like that have been known, chunks of that size have been known to be discharged in the most violent eruptions. So that kind of gives power to, or credence to how much power a volcano has. Okay, and then coming back to pumice. So pumice is a rock that is pyroclastic material. Basically, all it is kind of like a big chunk of material that it's typically formed from a more viscous lava, so a thicker lava. And what you'll notice is a lot of air bubbles here on the outside. Okay, the inside looks exactly the same, but what I want you to know is that the air bubbles on the inside, the gases are trapped in there. Okay, so they're not going anywhere. But then you've got these holes on the outside, which once did hold gases. But yeah, basically, the rock itself is it's made up of mostly voids, okay, voids with gases, and it's so lightweight that it will actually float in water. Okay, so if you ever get the chance to play with pumice, put it in some water and it will float. Okay, so are there any questions on the material, the pyroclastic material classification? Okay. All right, well then let's talk about the structure of a volcano. So you're going to see that there are 3 different types of volcanoes, and they all have the same structure essentially. What really differentiates them is mainly size. Okay, but anyways, we'll get into that. So first, let's start out with the pipe, also known as a conduit. Okay, that's that main area, that main kind of tube area that that every kid knows that is what feeds the lava up to the top of the volcano. Okay, so it's the main lava tube essentially. Up at the very top of the conduit / pipe, whatever you want to call it, is the vent. Okay, the vent is the end of the conduit where both the lava and the pyroclastic material will discharge from. Okay. Then there's a crater, which is basically right next to the pipe itself. The pipe itself actually ends at a crater. So the crater is that kind of bowl-shaped appearance. If you ever see a volcano from the top looking down at the top of it, you'll notice that kind of bowl shape. Okay, that's the crater. Okay, then you also have what's called parasitic cones. Okay, that's kind of these branches of lava that you're seeing, kind of taking a side journey from the main pipe and then heading off to the side of the volcano. Okay, These are basically like secondary um, uh, conduits for moving lava out of the volcano, okay? So not all the lava comes out of the top of a volcano, okay? That's a pretty common misconception, and understandably so, because that's how you would imagine it. Usually a substantial amount of lava will actually seep out the sides of volcanoes through these parasitic cones. Okay. And that acts to also help reduce the pressure of the lava that's going up to the vent, because if there weren't parasitic cones to help discharge some of the liquid, there would be a whole lot more pressure added to the main conduit here. So they're they're very helpful. Then there's fumaroles. Those, let's see, it's not shown on this picture, but fumaroles are just simply gas vents. Okay, they're typically found on the sides of mountains, or volcanoes rather. Typically, fumaroles they just form in cracks. So there will be cracks within the volcano that open up, and then gases and sometimes lava will just vent out through these fumaroles. Okay, so it's also another way that volcanoes help reduce the pressure that's being exerted by getting rid of some of that gas, because we know that gases play a very important role when it comes to violent eruptions. Okay, and then kind of an interesting feature for any of you, that have been to Crater Lake in Oregon, you've seen this, a caldera. So a caldera is basically an old volcano that erupted and then collapsed on itself. Okay, so by definition, the caldera itself is really this steep-walled circular area. Okay, in a lot of cases, there's a lake that fills in. Okay, but really, what a caldera is, let me just kind of quickly go through this picture here to explain it. So you have a volcano with a big magma chamber underground beneath it. And what you're seeing is during an eruption, magma is being shoved up to the volcano. It's being discharged out of the volcano. And that's emptying the magma chamber, which is what you're seeing here. This gray area represents a partially emptied magma chamber. So what happens when you get a partially emptied magma chamber is you're reducing essentially you're reducing the pressure. So you're taking the pressure off the top of the magma chamber right here. Okay. Whereas before, up here, you notice that all this liquid magma would be pushing up against the roof of the magma chamber. Okay, and that's what's holding up the volcano. But once that lava disappears or gets shoved up to the volcano, a void essentially opens up, and the roof of the magma chamber becomes unsupported. And as a result, typically what will happen is if the volcano will come crashing down into the magma chamber itself, and that will result in down here what you see is the caldera. So it's basically it's a very steep-sided circular feature, typically, because volcanoes are often very circular shaped. And in this case, the lake filled in with water, and then what you can see here, right here, is resurgence of volcanic activity, as this would essentially be kind of like a secondary vent right here. So basically, I guess let's just leave it as being called resurgent in volcanism. Okay, so we're seeing that even though that volcano collapsed down into the magma chamber, many years later, thousands of years later, volcanism is now renewing again. So it's kind of a ongoing process. All right. So let's take a look at the 3 different volcano types. Okay, so first is shield volcano. So these are very broad, big, slightly domed volcanoes. You can see that they have a very, very small angle that they slope. Okay, and these types of volcanoes will discharge low viscosity lava. Okay, so more runny type lava. And because it's runny, that's really what makes it this kind of very broad, slightly doming shape. It's kind of almost like when the lava comes out, it just essentially runs off on that kind of downhill under the influence of gravity. So it makes it just very gentle. Okay, so shield volcanoes are the largest of the 3. Okay, and just to show you how large these are, what you're looking at here is a picture of the island of Hawaii. That is the current island that the mantle hotspot is currently centered under. Okay, if you recall, I also referred that as a mantle plume. So what a mantle plume is, again, is basically just a rogue, kind of like a rogue fast highway for lava that goes from the lower mantle straight up to the surface. Okay, how they occur and why they occur isn't completely known, but they're rare, and that's probably partially why they're not well understood. But Hawaii is one instance, one of only a few instances where this happens, and it happens in the middle of the Pacific Plate, which is very rare. We know that most Earth processes, most geological processes occur at plate boundaries. Okay, so when they happen in the middle of a plate, that means that something is off. It's some different process. But anyways, getting back to the main thought here. So what we have here on the main island of Hawaii, which is right above where this hot spot is, we actually have 5 individual shield volcanoes. Okay, it's those 5 volcanoes and their lava that has actually made that big island. Okay, so that just goes to show you how big each shield volcano is. The second type is called a cinder cone. Cinder cones are basically, they're built up from pyroclastic material that has been basically ejected from the vent, okay, from the top of the pipe. These typically aren't eruptive, partly because they usually have the same type of lava that the Hawaii volcanoes have, that basaltic, very low viscosity lava, okay, the type that flows pretty quickly, water-like. And then in addition to material coming out of the top, lava out from the sides as well, okay? And what happens is how these volcanoes build up in size is that when they eject pyroclastic material and lava, anything that comes out the top settles on the flank, okay, on the sides. And that just adds to the overall size of the volcano. So each successive eruption, the volcano, gets a little bit bigger, but not a whole lot, but a little bit. So cinder cones are kind of interesting because they don't form at plate boundaries either. But I'll tell you when I tell you why, it'll make sense, or why, why they happen. So kind of stepping back, you've got the Rockies, and then you've got the Sierra Nevada mountains in California, okay? And those are two huge, very heavy mountain ranges. They weigh a lot, so they put a lot of weight on the crust of the earth, okay, on the continental crust. What's happening is they're actually pushing down the crust, which is resulting in kind of an arching appearance in some of the lands between them, okay? We call this area the Basin and Range Province, also called the Great Basin, okay? Two terms for the same exact place. Mainly areas like Nevada, the Mojave Desert, parts of Utah, Arizona, yeah, mainly those areas. So what's happening is you get that arching appearance, and basically cracks begin to form because the crust is being arched upward. So you get cracking in the crust. Okay, and when you get cracking, that means it's a fast track for lava to come to the surface. And so that's exactly what happens is you get lava straight up to the surface through these cracks that form. And that's how these cinder cones form, is because of the lava that is fed from these cracks. They tend to form in groups, okay? And that's because, of the crack. We know that if there are more cracks in a certain area in the crust, we know that there's going to be more cinder cones in that area because there's more ways that lava can be discharged out to the surface. Okay, so it all is a result of those cracks. Okay, and if you want to do more research, the term is tensional forces. Okay, it's really tensional forces occurring, out in the Great Basin. It's really kind of stretching of the crust and cracking it at the same time. Okay, so we won't get into the into the deepness of crustal thinning, but that is essentially what's causing this type of volcano to happen. Then the last type is called a composite cone, also referred to as a stratovolcano. So this type of volcano is what forms at convergent plate boundaries. So if you recall, a continental volcanic arc, that is where these form. So composite cones are the volcanic mountains that make up a continental volcanic arc. So that linear mountain range that runs parallel to the plate boundary. Okay. So size-wise, these are in between shield volcanoes and cinder cones. So they're bigger than cinder cones. Very similar to the structure of a cinder cone, because they're made up of usually combination of bedded lavas and pyroclastic material. So basically, again, during eruptions, you get some lava that's discharged, and you get pyroclastic material, which is this kind of ash cloud that you're seeing. That stuff will settle down into the lava, and it'll solidify. Okay, and over time, you can see this kind of layering in the volcano. Over time, for every eruption, you build up one more layer, and the volcano gets a little bit bigger. So in this situation, the viscosity of this lava is on the higher end of the spectrum. Okay, if you recall, I said that in the Cascades, for instance, which is the continental volcanic arc that extends from Washington down through Oregon and into Northern California. Those are compositionally they're andesitic or intermediate. Okay, so the rocks that you would typically find in the cascades would be diorite and andesite. And because they're intermediate, the viscosity is kind of a middle ground. But interesting enough, it appears that this middle ground viscosity is the most prone for violent eruptions. Okay, the very high viscosity lava, which occurs in other places, what often happens is that when that volcano goes to erupt, because the magma is so viscous, so thick, it tends to actually just gum up the system and not actually erupt at all. So that's kind of the odd thing about the super high viscosity stuff. So it's really this intermediate lava that is super important, because we know that just something about that specific amount of viscosity, that it makes these specific volcanoes prone to violent eruptions. Okay. Another thing is that they're also highly gaseous. So in addition to being pretty silica rich, they also contain gases, those volatiles, dissolved gases that we talked about, up in the 3 to 5% range. So up on the higher end of the spectrum. So having said that, we know that gases tend to affect explosiveness. So we know that when you put together the high gas content and the high silica content, that just seems to be a recipe for a violent eruption. Okay, so that's kind of the cone. What you're seeing here is a picture of the three, the size-wise. The Shield volcano is just large, it's huge. Here's the composite cone down here for letter B. Letter C is the cinder cone, okay? So cinder cones are really dinky. You can, if you ever find one out west, they're really pretty steep to climb up, but you can do it, okay? Just bring yourself a really good pair of boots, because anytime you walk on any volcanic material, that stuff is really jagged. It'll eat up your boots. So anyways, getting off topic there. So this chart is probably the most important asset that you have to understand volcanoes. So what I want you to do is come back to this chart before the midterm, and I want you to be able to understand it. All you need to know is these first 4 columns, 2, 3, 4. These last 2, don't even worry about, okay? That stuff's not really important. But what is important is how you break these down. So you have silica content, viscosity, and gas content. Okay, so I went through and talked about how those 3 of those affect explosiveness, and how they also affect the both the composition and thickness, or the viscosity. So this chart is very good, because it'll allow you to see how these different variables interact, essentially. You have a question? So which 3? I assume you mean which 3 volcanoes? So Shield, cinder cone, Shield, cinder cone, and composite cone. Those are the 3 types of volcanoes. Okay, I'll stop here. Are there any other questions relating to anything that we looked at with volcanoes? Because next we're going to kind of veer off the subject of volcanoes, at least the composition and structure. Okay. All right. So now we're going to talk about some of the effects of pyroclastic material. Okay. Now, keep in mind these concepts are associated with composite cones. Okay. Though actually, the lahar could occur theoretically for any of them as long as they're big enough, but at the risk of confusing everybody, let's just say that they're associated with composite volcanoes. So we have two types of pyroclastic concepts here. So one is called a Noé ardent, so more easily referred to as pyroclastic flow. So that's basically this big gas cloud that you're seeing here. So that's really just an ash and gas cloud, okay? What happens is during the eruption, a lot of ash and gas, very hot stuff, gets discharged from the volcano and will often not only get discharged up in the air, but a substantial amount of it will actually come speeding down the sides of the volcano. And that's what you're seeing here, is that's running down the sides of a volcano and spreading outward. So basically a big ash cloud, super hot, okay? You're not able to really outrun. They're super fast, and pretty much anything that gets in their way gets burnt to a crisp, okay? So you might Google pictures of Mount St. Helens after the 1980 eruption, and what you'll see is what was vibrant pine forests around the area were turned into big charred messes, okay, because of these pyroclastic flows that occurred, okay, basically burnt the heck out of everything. Then there's something called a lahar. So lahars really only occur at composite volcanoes. Well, geez, they could occur on shield volcanoes as well because they are big enough. But they're most known to occur at composite volcanoes because in order for a lahar to occur, you have to have a high enough mountain that it has a glacier on the top of it. Okay. And the Cascades are well known to fit that setting. Okay, a lot of those volcanic mountains have glaciers. And basically what happens is, when a volcano erupts, it's hot. It's super hot. So it's going to melt that glacier. Okay, and what you end up with is a lot of water. And that water is sitting on very steep slopes. So it basically runs down the side, water runs down the sides of the volcano very fast. And as it's doing that, it will pick up any material that's in its way. So ash, other pyroclastic material, trees, rocks. I mean, if it's moving fast enough, it can pick up some rocks, and it will just pick up all that material and move it downhill, okay? So typically with a lahar, they will end up discharging in a stream valley. Okay? And this picture down here, you're seeing that all these logs, these trees, they were probably uprooted and carried downhill and deposited in this stream channel. But what you may not notice is these trees in the background, they were spared, but you can see how high this ash-rich kind of mud flow material reached on the trees. Pretty high. There's a person over here for scale wearing some sort of yellow, perhaps rain suit. So you can probably assume this is a good 15, 20 feet above the ground surface, not including the stream channel. So this kind of soupy mix of mud and trees and you name it, any other pyroclastic material, uh, it, it just wipes out everything in its way. Okay, bridges would be wiped out, roads, houses. Um, yeah, they're very, very destructive. Okay. All right. So now we're going to kind of shift gears here. We're going to look at other types of volcanism that aren't specifically volcanoes. Okay, so this is the other extrusive igneous activity part of the chapter. So I had mentioned that in the western U.S., the Basin Range, Great Basin area, you have cracking in the crust. Okay. Okay. In that situation where lava comes up to the surface through those cracks, yes, it can form a cinder cone, but it doesn't always do that. Oftentimes, it will come up to, and it will, lava will just kind of spread out into sheet-like form. Okay, these fissure eruptions, they tend to be basaltic magma. So they tend, or rather basaltic lava. They tend to be very low viscosity, so more water-like, runny type lava. So they come out of the cracks and they just kind of form flat sheets. You can see that right here. Okay, you can see individual sheets that are stacked up on top of each other. So that means that new fissure eruptions, so newer episodes of volcanism have been laid up on top of older instances of volcanism. Okay. Okay, then there's a couple features that you can see. Let's see. Let me start with columnar joints down here. So columnar joints are this picture up here. I don't know how these pictures keep getting mixed up, but what you'll notice is that they look like columns that are six-sided, okay, or hexagonal. Okay, that's how basalt cools. It cools in this six-sided column appearance. Okay. For any of you that have been to Devil's Tower in Wyoming or plan to, basically you're going to see columnar joints. Okay, if you go up really close, it looks like scratch marks. Okay, those scratch marks are actually these columnar joints. But the main thing at Devil's Tower is this thing called a columnar, a volcanic neck. Okay, that's down here. A volcanic neck is merely just the pipe, the leftover remnants of an old volcano. And really, it's just the pipe or the volcanic neck of the old volcano that's left. And the reason that happens is because we've seen that when volcanoes erupt, they often discharge lava and pyroclastic material that kind of add to the sides of the volcano. Okay, that's what makes layers of the exterior of the volcano, and that stuff's pretty easy to weather and erode. Okay, we haven't gone over the concepts of weathering and erosion yet, but basically it's Mother Nature's way of breaking down material and turning it into fine fat fragments like sands and silts. So what we end up is over a long period of time, Mother Nature breaks down the material of the volcano, breaks down the weak stuff, which is the outsides of the volcano. And what it leaves is that very durable pipe, which is made up of very durable igneous rock. Okay, very hard to break down. So what you're seeing here is essentially a pipe, an old pipe from an old volcano. Okay, so that's a volcanic neck. Devil's Tower is also a volcanic neck. as is shiprock in New Mexico. Okay. Okay, and then associated with volcanic necks oftentimes are what geologists call intrusions. So intrusions are just simply pressurized magma that gets shoved up into cracks in pre-existing rock. Remember, magma has tremendous pressure put down on it from all the rock above. And so when you put pressure on any liquid, think like hydraulic fluid, for instance, that liquid will be forced up into any tiny crack, and that's basically what intrusions are, these tiny cracks. So intrusions can be flat or they can be up and down, okay? Mainly terminology here, okay? So when we have an intrusion that goes down, it's referred to as a dike. Okay, so a dike means that the intrusion is cutting across existing rock strata, so existing rock units. Okay, dikes are also referred to as discordant. Discordant basically means that they cut across rock units. Okay, but the intrusion itself is referred to as a dike. Then you have what's called a sill. Sills are concordant. That means that the intrusion occurs flat or parallel to the bedding of these individual rock strata. So they just kind of fill into those spaces in between the rock units, typically. Let's see here. So if we go back to this picture here, what we're actually seeing is, here's the volcanic neck. Here are some dikes. Okay. So oftentimes, if you're out west, especially in the basin and range area, if you see what looks like just kind of like almost like the spikes on a dinosaur, the top of a dinosaur, you know, those spiky plates, kind of like a line of those spiky plates out in the middle of nowhere where everything else is flat next to it. Okay. Those are definitely dikes. Okay, so those are always kind of cool to check out if you have the opportunity. So yeah, those are intrusions. Also tend to be made up of pretty durable igneous rocks, so they don't weather and erode very easily. Oh, okay. Guess that's it for this chapter. So let me see here. Okay. So are there any questions on anything that we looked at today? Okay, I'll take that as a no. So then we will regroup next Wednesday, and we'll cover chapters 7 and 8. So we'll look at crustal deformation, mountain building, weathering, soil, and mass wasting. So really just kind of a hodgepodge of different topics. Okay. So yeah. So everybody have a good weekend, and see you next Wednesday.
Thank you. Have a good weekend.
Thank you.